Hello, everyone. Thanks so much for joining. My name is Em. I do marketing stuff here at Upstream Tech. I'm really excited to be hosting this panel with Laura, who is our head of product for HydroForecast, and David Payne, who is principal hydrologist for Mercury in New Zealand. We're going to go ahead and get started. We pre-recorded the main portion just for the sake of our New Zealand folk. So we're going to be playing the presentation, and then we'll be hosting a Q&A at the end. So we're going to go ahead and get started with that. And all right.
Hi, my name's David Payne. I'm the principal hydrologist at Mercury, and I, along with Ben Colcord, who is the technical lead for the data science group at Mercury, I'm going to give a presentation on how we use forecast inflows from Upstream Tech. So what are we going to talk about? Who we are, where we are located, and a little bit about our portfolio, the evolution of our inflow forecast, and how forecasts are used for dam safety. I'm going to do that bit, and then Ben's going to cover over how the forecasts are used for the Digital River tool. So what are we? So we're both a generator and a retailer. I'm not sure how it works in other parts of the world, but we can generate power and we can sell power to customers. Now there is a transpower, so there is a middleman to make sure everything is above board, and we put that into a wholesale market. So we generate power to that market, and then our retail arm buys power off that market. So that's how the two halves work. We have a portfolio of hydro, wind, and geothermal. So wind is capacity is 750 megawatts. Hydro is 1084, and geothermal is 510, totaling approximately 2,344. And we are 100% renewable generation. So from those three assets. And we sort of broadened out a bit. And now we're getting into telecommunications as well. So that is broadband, internet, and phone lines. So a new addition to our suite of opportunities. Locations. So this is a map, part of a map of the world. You can see the top right-hand corner is the United States. I think everybody knows where the United States is. And in the bottom left-hand corner, you can see Australia, the land from down under. And if you look across to the bottom right, you'll see two islands, three, but there's two to see. And that is New Zealand, and the Tasman Sea is in between us and Australia. So this is New Zealand. There's a bottom island called Stewart Island, and then there's South Island and the North Island, top one north, bottom south. Obviously the person who named that wasn't that imaginative. And you can also see that the North Island is shaped, or some say, shaped a bit like a deer, pointy nose to the left, ear to the right, antlers to the north, and the neck to the south. And a little blue dot is in the middle of the island, which is Lake Taupo, which is our storage lake. The deer had nothing to do with the presentation, but I just thought I'd put that in there for interest's sake. So the Waikato hydro system, you can see that the lake, our storage lake, Lake Taupo, is at the bottom of our scheme. The river runs north, heading out to the west coast of New Zealand, and there's a map on the top right that shows you where we are at the North Island. And the river runs north, and on the map you can see there's little white semicircles. They are our dams. Owakuri is a second semicircle, and that has a 12-hour travel time, but pretty much all the other dams only have an hour between each of them. So the water goes through our cascade pretty fast. So, you know, inflow forecasts are quite important. And we also have the tributaries that come into the catchment basically you've only got 3 or 4 hours travel time. So basically all the water's going to turn up very fast. And then you have the wiper on the bottom left that also comes in, which is slow moving. So you're trying to, the forecast is trying to help you not have the Waipa and the Waikato River inflow at the same time and merge, because then you have lots of flooding down the lower Waikato River. So important to understand the flow of water and when water is arriving. So, and here is a scheme elevation. So you've got Lake Taupo at 350 meters, Karapiro Tail Race at 24. And you see that diagram has pretty much flat lines for lake level for the rest of the dams, hydro dams there, hydro lakes. And that is pretty much actually how it works at night when we shut down, because less people want power. And so the headwater level is equal to the tailwater level of the station above, up a little bit up towards Owakuri. Okay, so evolution of inflow forecasts. So we've had a few rainfall runoff models over the years. None of them very good. They didn't really estimate inflows into the hydro system very well, so there was not much faith in them. Mercury belonged to CIATI. Now, I think most of you know about CIATI. I'm told you do. And so CIATI ran a contest where entities competed for a short-term 1-year inflow forecast, 19 locations in Canada and the States. 25 categories in that contest, and Upstream Tech won 23 of them. So basically, I thought, well, that's pretty good. So I have to have a talk to these guys. And I sort of suggested that, well, that's all very good, but that's in America, and New Zealand is different. We're a different part of the world. So how about you prove, Upstream Tech prove that you can do it, and then if it's all right, we'll take up a subscription. So sent all our tributary data over, Upstream Tech ran the AI models, and basically proved that they could forecast inflows for the hydro system. So we started the subscription, and as soon as we started the subscription, it stopped raining. So I caused a drought, and we still have low flows. We have low winter flows. So we haven't really had a huge storm in anger that basically could have a look at the inflows, but it's looking good for what we've had so far. And the thing I like about the subscription is you don't have to worry about software. You don't have to worry about licenses. You don't have to, and you can basically, within reason, get out of the subscription if you don't need it anymore. So it's all good. So why do we need inflow estimation from a dam safety point of view? To maintain the dam integrity. So you get a rain, well, cyclones are our biggest problem actually, from either coming off the coast of Australia or down through the islands in the Pacific. So a cyclone turns up, and we've never had an inflow estimation really before that could give us any indication of what the volume of that inflow would be, because one of our dam safety mitigations is to draw down the hydro system. So we discharge water days before, create some storage for the incoming flood volume. So basically with the forecast inflow, I can work out a volume, and I can figure out how much volume will come in and how much we have to draw down to accommodate that volume, flood volume. Obviously, if say 25 million cubic meters was coming in, I wouldn't just create a hole for 25 million, because there's a bit of error associated with that. So be conservative, but it gives a good guide to what you think you're going to receive and how you should react, because for past floods, we've always found we've discharged way more water than we should, which basically comes at a cost. So, yep, and so that's good, thanks. So we have to pass the PMF. Our inflow design flood, if you like, is a probable maximum flood. That's the biggest flood that you can get. realistically, without catastrophic failure. So the water has to be stored. We can destroy lots of infrastructure, but we have to store the water, because downstream is Hamilton, 120,000 people below our last dam. And if we do really high discharges, we're going to flood probably 30 houses. So we have to be very careful that, we look at our flood management and we act responsible. And the inflow forecast helps us with that. And as I said before, the travel times between the hydro sites are only an hour. We've got fast tributary inflow, so water comes in pretty fast, and we have to manage that. And now I'm going to hand over to Ben, and he's going to talk about the inflows in the digital river.
Great, thanks, David. So I'll just talk a little bit about the electricity market in New Zealand. David's covered a bit of this already. So see, we're more than half hydro and majority renewable energy, and Mercury is a bit over 50% hydro and about a quarter wind and about a quarter geo. And so in a day-to-day running, the geothermal is pretty constant, but that wind can vary a lot, and it's up to the hydro to kind of fill a gap. So it's the hydro that goes up and down. So the electricity is sold on a market with half-hour trading periods. So the generators will basically sell electricity, and the retailers will buy it off the market. We happen to be both. And the plot there is showing, so the orange line is our net position, which is basically what we think our customers will require. And then our generation, we can decide to go above or below that line and either buy the difference from the market or sell it. So that's a kind of strategy decision depending on what we think the prices are doing. And yeah, the blue line there, which is the wind, kind of can wreak a little bit of havoc on that. But so the hydro kind of has to be able to react to whatever the wind does. And along the bottom there is our kind of digital model of our river. So we have 8 stations along the river, each with between 3 to 10 generating units. About 20 hours travel time along the entire river. But as David mentioned, there's 12 hours between the first 2 stations. So we kind of need to plan ahead. We kind of have the 2 peaks, the morning and afternoon peaks. We need to make sure that we get enough water into the river that we can generate for those. So we have to have good planning for those. There's also quite a large variation in the flow rates in the stations. So we can't just have everything flowing at the same rate, because our bigger stations can kind of overwhelm the smaller stations. So we need to have quite a good plan going. And also, apart from Lake Taupō, which is the large lake at the top, we don't really have much storage. So kind of have to use the water rather than store it. And about 2/3 of the water that goes into the river we get from tributaries, which is what we're getting the forecast for. So it's really important that we get accurate tributary flows. And in this diagram at the bottom, along the top are this is just a snapshot. So you can see the flow rates coming into those tributaries, and that line along the middle with the flow rates is the flows through the stations. And yeah, so that those tributaries, we get all of those forecasts from the Upstream Tech HydroForecast. So yeah, it's kind of our main input into this model. Now, hydro planning is quite complex in that there's quite a lot of things to consider. So we have a planned generation, but it can change. The wind changes. If there's a change in the market price, we might want to change how much we're generating. And sometimes there'll be changes in our tactics in terms of pricing and things like that. There's also a lot of constraints that we have to abide by. So we'll have maintenance, sometimes planned, sometimes unplanned. So units will be unavailable, things like that. Obviously, any kind of dam safety is very important. And then there's also environmental and community constraints. So the river is kind of a publicly available resource for people to use. So people kayaking on the river want to make sure it's safe for them. We don't want the river going too low or too high for environmental reasons. Can have an impact on the ecosystem and things like that. And traditionally, the actual efficiency is not the number one priority in terms of like an optimized kind of squeeze the last drop of efficiency, which is what this model is trying to do. Instead, we try to avoid spill and keep the river in a good shape. So that means keep all the reservoirs in a state where we can be pretty confident that whatever happens, we'll be able to respond to any changes. And so all the whatever comes, we can generate what we need. But with our optimizer, we're trying to kind of push some of those limits and basically trying to find areas where we can increase that efficiency and still meet all our requirements and constraints. So with the model that we have, if we know for a certain trading period that we need to generate a certain amount of megawatts, we know what the headwater levels are on all of our lakes, we know which units are available. It's pretty straightforward to work out the most efficient way to generate that power. But if we do that every half hour, then eventually we're going to start breaching all of our constraints. So that's not actually a very good plan. It's efficient for the very short term, but it's not an actual reliable plan. So what we've done is we've kind of created an iterative solver that considers not all yet, but most of the important constraints. And we find a solution that gives a very good efficiency. The plot there shows the headwater levels variation through our plans, through one of our plans. And we create a new plan. It's a 7-day long plan. And we create one every half hour. So every trading period, we get a new plan, which would have all the latest changes. And so the benefit of this tool is it gives better efficiencies than what we typically see with what the actual hydro controllers do, and even a 1% improvement is about $5 million a year in water savings. But because it's not considering all of the different things at the moment, we can't just enforce people follow the plan. So there's a lot of potential there. And one of the ways it's useful is to review a shift. So our hydro controllers do 12-hour shifts, and then we can afterwards compare what actually happened to what our plan had suggested. We can see why things varied. Often there's good reasons for that. There were things that changed that our plan didn't know about, or other things. And there's also learning new ways to respond. So our plans, for example, typically will use a much wider range of the headwater levels than our hydro controllers would typically be comfortable with doing. And we're potentially building up a bit more confidence in using that extra range, because they generally can come with some efficiency gains overall, and still retain most of the flexibility. And sorry, can you go back? Yeah, we also, for medium-term planning, we can also look at the headwater level, or the water levels in our main reservoir, Lake Taupo. So we get by having the accurate tributary inflows, then we've got a pretty accurate estimate of how much water we will be taking from the lake, and then how much that lake will be varying as well. So and that drives a lot of our pricing. So if the lake is nearly full, that means we need to flow more, and the prices will go down. If it's nearly empty, we need to hold back, and the prices will go up. So it helps a lot with our pricing. And then some of the future plans for this tool is really just longer term planning. So 2 weeks up to maybe a year, where we do some kind of A/B testing. So we could, by running one simulation with certain units available and unavailable, we can get an estimated cost of how much that maintenance will actually cost us. Or for say a unit upgrade, which may have the unit out for months at a time, we could estimate the cost benefit of actually upgrading a unit. And we also could potentially, at the moment, the amount that we're generating is an input into our plan, so the generation demand, but we could combine with maybe our pricing and demand models to create an overall profit optimizer instead of the efficiency optimizer. So there's scope there to kind of improve on it. And I'll pass back to David to talk about this possible future project.
Yeah. So Lake Taupo, our storage lake, it's actually the townsfolk and have built quite, or the district council let the townspeople build quite close to the water's edge. So there's some flooding issues associated with that, and also for the lake, a competitor, Genesis, diverts water from another catchment and it goes into the lake, and also they run a power station into the lake. So we have a managed inflow and an unmanaged inflow because there's some large tributaries into the lake. And one of the things is the regional council, who is our regulator, and we have consents to operate on that lake. You guys probably call them licenses. We basically have to abide by those consents, and our competitors look at our consents and make sure we're doing that. So there's I guess a multi-agency managing that lake, or checking that we do things correctly with our consents on that lake. So it has been suggested that we have a combined Lake Taupo inflow model. So we'd all chip in some dollars for that. But the problem is that to get that, you have to get some of the Genesis data, which is commercially sensitive. Under our Commerce Act, we can't basically help each other out. So an option would be that Upstream Tech provide an inflow forecast for the 22 catchments going to Lake Taupo, and then Genesis provide them with the unnatural inflow, combine it together and give all three entities a forecast inflow. And that would be pretty good, because then we would know what the forecast inflow, and we could work out based on our outflow, the demand and the lake level, and each person could do that. And yeah, basically it would provide a solution to us. So I think that would be quite interesting, and we're going to explore that one. So that's about us done, and I guess we'll open it up now. So are there any questions? And yeah, basically it would provide a solution to us. So I think that would be quite interesting, and we're going to explore that one. So that's about us done, and I guess we'll open it up now. So are there any questions?
Ben, I had a question about what y'all are currently using at Lake Taupo and the improvement that you see that a forecast or a different way could make.
Yeah, so we have a LSTM model, so kind of machine learning model based on the data that we have, but the data is actually quite spiky, and the problem is that we kind of calculating the Lake Taupo inflows on headwater levels, and a very small variation in the lake headwater level, because it's so large, really causes a lot of noise in our inflow number that we get from the data. And also, as David mentioned, there's some of the flow is not natural, and so it can be held back, or if they decide to generate more, then that'll increase. So we can't really predict it that well. So being able to get a proper model that considers all of those other inflows and models of that, I think would be a great improvement.
Sweet. So that was the full presentation. We do actually have David and Ben both on the call, who are joining us very early from New Zealand. So we will open it up for Q&A. We have a couple questions coming in through the chat. I'll read the first one. How are you measuring 1% efficiency improvement? Great question.
So we have kind of what we call a reference value for every station that we are comparing to, basically a megawatt per cubic, and so we can calculate that for all our flows, and we can look at what has been done historically and compare it to that same value for our plan. So it's just comparing those two efficiency values, basically, the actuals and what our plan said. Yeah, basically the megawatts in the QMX gives us an efficiency.
One thing that actually we found too that I didn't mention in the presentation is that the forecast inflows are probably better than our scaled tributary flow, because we can't measure the whole catchment, so we scale our tribs to get scaled tributary inflow, and the forecast inflow is better. So now we have a mismatch between what we see in real time and what we see in forecast time. So we're going to have a look at that. And also, now we're getting the forecast inflows, we need to have a look at the actual weather forecast. So it just opened up a few more things for us to have a look at.
Sweet. We got another question. Question for David and Ben. You mentioned that wind has a big impact on generation and also a factor that's difficult to predict. Do you rely on any specific wind forecast currently, and how do you factor that into your decisions?
We do have a wind forecast. To be honest, I'm not 100% sure of the source. I see the data in the database. There's probably better people to answer. Yeah, we know that the wind that we think is coming will. So when that goes up, then the amount we expect to generate with hydro will go down. But when that changes, there's kind of a double impact. Because if the wind goes up even higher, then we will need to generate less just to cover our demand, but that also pushes the price down. So we may want to generate even less because we're getting less money for our water, essentially. So yeah, we do have a forecast. Sorry, I'm not sure of the source, but yeah, it does impact our plan a lot.
All right, sweet. Well, if there are any other questions, please feel free to follow up with us through our email, team@hydroforecast.com. But thank you all so much for joining. Thank you so much, David and Ben, for joining us all the way from New Zealand. Yeah, and we will also be sharing out this recording in a couple of days. Thanks, everyone.
Cool.
Thank you. See ya.
Bye, y'all.